My name is Juanpe. I am a C++ developer based in Berlin. I work as a freelancer, doing contracting and consulting jobs around modern C++ and interactive software. And one of my focus lines of works and the things that preoccupies me the most is trying to make value semantics scale to the level of architectural thinking, which I think is hard in C++. I think most people in this room probably kind of like value semantics. Who here likes value semantics? Yeah, almost everyone, right? And who works in a code base where most types are value types? 2 persons that think this is a Haskell conference. It's hard. It's hard to do in C++. So that's why the first part of this talk is called the tragedy of the value-based architecture. So if we want to have a value-based architecture, we start by modeling the data model of this. Let's say we're writing an interactive application for desktop using value types. So this is a nice value types, which is a tree of vector, maps, tuples, and structs. Simple, copyable types. Now, thanks to this, when we want to write our application logic, we can do it using pure functions. Functions that you cannot see with a contract here, but here there is a pure function that takes the document by value and returns the document by value. I don't know if we can put this down or turn. Maybe we can turn some of the lights off or something. Anyways, here there is a pure function that takes a document by value and returns the document by value. And even though it does some update of the data in itself, the copies protect the data. This is a pure function. There are no side effects. It's very easy to write, verify, and test. Now, with these value types, we can also implement features that are otherwise complicated in a very simple way, like an undo history just becomes an STD vector of all the states of the application, right? With all the versions of the documents, with all the edits, simply stored in this vector. Now, if we want to add parallelism with a render thread, we can just have another thread where there is here, you probably cannot see it, but there is a while loop that is simply fetching through some channel a copy of the document and then rendering it to the screen so we present it to the user. If we want to do something like persistence, we can simply launch an asynchronous task that just captures the document by value. You probably cannot see it here, but here there is an std async with a lambda that captures the document by value, and then that's the saving in another thread. And the simple capture already does the copy, and everything is safe, no mutexes or anything. Now, we can also then add more representations for the document. So I worked a lot making music software. We often have a sonic representation of the document, so an audio thread that also wants to consume this document, transform it so we can emit audio. And again, we can probably get a copy of the document and operate on it. Now, as C++ developers, we see, if these are value types, these are these copies, this simply does not work. As soon as your document is not trivial, we have copies all over the place, this doesn't work. So as a good C++ developer, I'm going to start saying, well, let's not do things, by value. I get the document and return it by value. I get a reference to the document, I update it in place, and this function, instead of being a pure function, it's a function that operates through side effects. But as soon as I do this little change in this function, this document, it doesn't become, it's not a value anymore, right? Even though it may have a value, we're thinking of it as an object, as a location where I put the data in. Once it becomes a location, then we need to think about who is looking at this location at a moment in time. So the render thread needs probably complicated locking mechanisms, and to be able to deal with it efficiently, we have an intermediate representation for a UI in the form of an object tree. We also need to update this representation of the UI. So of course we need to add some listeners and signals calling back to update the data model or to update the views when the data model changes. We also cannot do the nice history by just copying the values. We need some command pattern that implements the operations twice, one in one direction and then in the other direction. We cannot do the persistence asynchronously because it's, the user is editing. We cannot really do this, so the user is just gonna see a spinning clock. They're already used to this, but nothing is gonna save us from the flying spaghetti code monster that took over our code. Okay, so we really went down this rabbit hole because there was too much copying, right? So copying was a problem, and we thought, well, as C++ developers, we are hardwired to think that passing by value means copying. So value semantics don't work. But that's not really the case. The implication is that when you have mutability, then passing by value means copying. Because, of course, to preserve the value that was there, you need to make a copy such that other people that mutated, the side effects are not visible in the other values. But if you remove mutability, you can pass by value without copying, right? I can just pass a pointer to this data, and its value is not going to change, as nobody's allowed to change it. So we can then build tools around this principle. So we can have data structures like this magic vector that I can mark always const, and I can still do things with it. For example, I can push back data. And when I push back data, instead of modifying the first variable, which of course is const, it returns a new version of the vector with the data updated. I can do this again and again. I can also, of course, update the data. So in this case, we cannot use this traditional syntax because we need to get a new vector. So we use the set method that then returns another version with the value updated. Now with this, we achieve a property that is called persistence. This is not persistence as in saving to files. It comes from the data structure world. It means that the previous values are preserved. So we can compare the different versions of the values. This allows us to reason about change, right? Because we have the previous and the current value. This is very useful when writing interactive software. And this allows also a property called structural sharing, which is that all these versions of the vector, even though they look semantically like completely distinct copies, they can share data under the hood because of this immutability that I just mentioned. So I really wanted these data structures to exist. So in the end, I built a library myself. I'm going to be presenting this library called Immer, which is a C++ library of immutable data structures. And the goals of these libraries is 3. So the first one is to be idiomatic, because there is a lot of work bringing functional programming concepts to C++ that in the end pretend that C++ is Haskell. And I think this is a big impediment for people really adopting these techniques. This tries to be more or less normal C++. The second thing is performant, right? Because if we're doing C++ to begin with, instead of some other languages, it's because we need performance. So we need to have the customizability as a third point to be able to adapt it to our environment and choose different, let's say, garbage collection strategies and whatnot. All right, so we can move to the part 2 in search of this magical vector. How does this magical vector that I just presented work? And before we move to vectors, I would like to show you the more traditional, the more common immutable data structure, which is the list, right? If any one of you has ever programmed Lisp or any other functional programming language, this is the bread and butter of functional programming and immutable data structures. So if I have an immutable list, I start, let's say, with this version 0 of a list that contains one element, which is the character A. I can push, let's say, 2 more elements, and I get this new version v1. Now, this new version includes the 2 new elements, but then has a pointer to the element of the first list. This is the structural sharing I was mentioning before. So the different versions of the data structure point to the same data. I can add another element, and I can also, let's say, fork the data structure. So the version 1, I make another version with a different element E. So we have 2, let's say, paths pointing in the end at the same fundamental data, right? This is the principle under which we avoid the copies in these data structures. And following this principle, there is a lot of interesting literature building such data structures. I think the seminal work is the purely functional data structures from Okazaki. I find really interesting also the finger trees. But all these data structures, they're built with functional programming languages in mind. So they are not so cache efficient. They're based in small nodes. We all know as C++ programmer that lists, like the one I showed, they're not very efficient. But there was some groundbreaking work by Phil Bagwell that introduced these array mapped trees that then were, I would say, popularized by Rich Hickey, who is the author of the language Closure, which I find it a really interesting language and a very influential person, because he basically said, okay, I'm going to make a Lisp language that is not going to be based on lists as a fundamental data structure. It's going to be based on vectors. And it's going to be based on vectors that are, although still immutable and efficient, and provide this structural sharing and whatnot. So let's see how these vectors do work. So to implement a vector, ideally, we will have a contiguous array of data, right? This is the most cache-efficient data structure we can have. But with this, we cannot have a structural sharing, because if I update one element, I have to make a copy of the whole array to get a new version of the data. So we can make a compromise by slicing the vector into chunks. Now we have a chunk of small arrays. They are now floating in the space. This is not a data structure. We have to assemble them somehow. Well, we assemble them again in the most efficient data structure, in an array. This array, again, is maybe too big. What do? We slice it again, and again, we assemble it in another array. This data structure that we form by slicing the data in chunks of a fixed amount of elements, that is a power of 2, is called the Radix Balanced Tree. And it's characterized by this branching factor, so the number of elements in every chunk, that is a power of 2. Now, in the slides, I'm using a power of 2 with a b equals 2 and 4 elements, such that it fits nicely in the slide and you can easily see what's going on. But in practice, we use chunks of 32 elements. And this has been shown to be experimentally a very good trade-off. And think about this, right? Because as C++ developers, you're thinking, well, this is a tree. Trees are not that efficient. There is indirection, But these trees, they grow very slowly. They are not like stdmap. They grow slowly. Actually, you can have every element that you can index with a 32 bits element with just 7 levels of depth. Now, when a tree grows so slowly, in the end, other factors, when you have big vectors, other factors like the cache size versus the amount of data that you have are going to have much more impact, actually, than the depth of the tree itself on performance. So, okay. Then how do we implement operations in this tree? Yeah? There's a question. Yes, I will talk about it later, actually. Yeah. But yeah, assuming we have now like normal, pointer-sized elements, and I will cover that case actually later. So let's say I want to access the element at the index 17. Well, what we do is we split the binary representation of this in groups of b bits. Now, every of these groups will tell us the index that we have to go in each of the levels of the tree. So we start in the first level, we go to the second level, and then we go to the third level. And in a very direct way, we have access to our element. Now let's say we want to update the vector, to get a new version with this element updated. Well, we're going to have to copy the chunk in which the element is located with the updated version. Then we're going to have to copy every parent up the tree, right? So we have copied certain amount of data, but we are also reusing a lot of data, right? This is the structural sharing we were mentioning that provides this compact representation of a sequence of operations. Now, there is another interesting thing we could do with this. This is a tree. And one of the things that one would think is easy to do with trees is concatenation, right? But this is not the case, because this tree is perfectly balanced, which means that this hole that is here, it's not allowed, right? If we concatenate a second tree here, we will need to copy the first element of the second tree in this hole, then we will have a hole in the other side, and then in the end we will have to move every element one by one from the second vector. So it will be a linear operation. But Phil Bagwell then found out that we can relax the tree and have nodes that are allowed to have less elements than they will have in a perfect balanced tree. Once you do this, now you can also define concatenation of vectors in logarithmic time. Once you have concatenation of vectors in logarithmic time and also slicing, you have insertion at any point in logarithmic time, which is very interesting. You don't get this with normal STD vectors. This is the relaxed Radix Balanced Tree, and this is the map of operations. We have effective O1 random access update and pushback. I say effective O1 because in reality it's logarithmic, but it's logarithmic to this depth that in practice, since it's not that deep, you can experimentally say, well, it's like effective O1 with maybe a big constant, but O1. Then there is a concatenation, insertion, and push from, which is actually really logarithmic. So this is nice. Now, there is still one problem, which is actually the problem that Vittorio mentioned. This is a picture I'm painting here. This data structure is normally implemented in JVM languages like Clojure, or in JavaScript there is also very used implementations where the picture is really like this, right? So every element is boxed and every element lives in their own heap space and the data structure is just pointing to these elements. But we are C++ developers. We want cache locality. We want to have the elements directly embedded in the leaf chunks of the system. Now, what happens if I have big elements? Well, the chunks become big. Now, this nice proportionality and balancing I had of the tree, it doesn't hold anymore. Now, the branching factor is not going to be good anymore. But if we adapt the branching factor, then you're going to get maybe very deep trees just to accommodate bigger elements of the leaf. So I modified the data structure to have two branching factors. And this is still possible, one for the leaf elements and one for the inner nodes. So if we have big elements, we just have less element at the leaves. If we have very small elements, like chars, we can also pack more at the leaves. And this way, the same properties hold for regardless of the size of the thing. And this is what I call the embedding relaxed balanced tree, which, as I said, it's characterized by having two different branching factors, and we can derive the ideal branching factor for the leaves from the relative size of the element to the size of a pointer.
Ideal under what when you say ideal, what do you mean under which category? What's the measure?
When I said?
When you say ideal, what are you
Ideal. Well, I say what I mean is that you can, for example, run experiments to see for a particular architecture what the best branching factor is by measuring update performance and lookup performance, because obviously lookup performance is best with higher branching factors, right? And it has an asymptote at the highest. But then update performance is actually like a curve. So then you can measure the two things and say, okay, my optimal branching factor balancing lookup and update is this one, right? And you can do this for the normal, for normal pointer size things, and using this rule, then you can extrapolate this to other types. Okay, so now we have a very nice data structure, but there are still, tricky things that we have to discuss about this. Let's look at this function. It's a very simple function that takes an immutable vector as an argument and returns a vector with every element, so every integer between first and last, appended to the vector. I'm not sure if everybody can see properly the code on the slide. Can the people on the back see it? No? Well, there is a loop here where we're just pushing back and returning, storing in the vector v the vector we just pushed back to. I guess the people at the front probably can see it, or no? Yeah. So does anybody see a problem with this function? Hmm? So one answer was we're returning a new vector, right? And
What is the immutable because like last is smaller than?
it's an infinite loop if last is smaller. Yeah, there is a precondition that is not explicit in the code that last must be bigger. Yeah. I'm trying to set an immutable variable. That's not true. The vector here is not marked as const. So these immutable vectors, they still have assignment operators. So you cannot mutate the data that's inside, but you can replace the whole vector by a new vector. Yeah, so one answer here was I'm filling the undo stack. Well, the old vector is going away, so it's being deallocated in the next iteration of the loop. So Vittorio said, we're not calling reserve. And it's true there is no reserve for this vector, but it goes in that direction. In the end, I think the problem with this function is that in every iteration of the loop, we are allocating some chunks in the rightmost side of the tree to put the new data. And in the next iteration, for 32 iterations every time, we're just creating a new copy and deallocating the previous one, right? So why not reuse the old vectors? For that, it's not the standard vector. Yeah, sorry. That was a comment. Yeah, it's confusing because it's also called vector, and I didn't put here. This is the immutable vector. It's not the standard vector. So there is a tool that I basically copied from the Clojure version of this, which is what's called transients. So you can ask a vector to give you a transient version of it. The transient version has the normal mutable API that std vector has, and it implements CppOnWrite such that, of course, it respects the immutability of the source vector, but it's allowed to do more efficient things when, for example, in this case, you push back a series of elements, it reuses the buffers that it just allocated and mutates them in place. At the end of the function, we call persistent to convert this mutable vector back into an immutable thing, right? So this function is like a transaction. We have mutation, but mutations are locked in this little nice function. From the outside world, this is still a pure function, yet an efficient one. The other nice thing about having this API is that this gives us some degree of compatibility with the standard algorithms and the rest of the C++ ecosystem that might be expecting, you know, a pushback that updates in place. Yes? The question is, what's the balancing of these trees? Well, the completely balanced version is very easy to balance. So as you add the data, it's always keeping the balance because you're adding it to the leftmost side and then putting new things. Then when you have concatenation, that is a very complicated algorithm that makes sure everything is enough balanced such that you still have efficient access. No, you don't have to do rebalance ever. So it's just the concatenation operation have to take care of not producing a concatenated vector that is unbalanced. Every other operation is trivially, keeps the balance in a trivial way. Anyways, there is this other code here where I have a function, say hi, and it calls pushback, pushback, pushback directly on the temporaries that are produced one after another. Now, this is interesting, this code, because here we have two types of values, right? So the first value is a named value, what we normally call an L value. I'm thinking of the value v, that is this variable, which is an argument also, and it's a local variable from the function. But then as you call pushback, this pushback returns a new vector that is an R value, it's an anonymous value. So you could think, well, if I have an anonymous value, and let's say the data, so these nodes that I have under the hood, let's say they have reference counting, and I see that a reference count is 1, so only this vector is pointing to that piece of data. If I mutate it, nobody's going to see it, right? It doesn't have a name. Nobody can reference this variable. So that's why in the library, actually, the garbage collection strategy is optional, but normally you will use reference counting. In the library, operating on our values is like operating on a transient. So actually, here there are not going to be 3 allocations. There is only going to be 1 on the first case, and then the second one will most probably reuse the buffer that was allocated in the previous one. Now we can go further in this function, of course. We can move the variable v, and now everything is an R value. We can do this because this is it's the last time we're using the name, right? And this is really cool, because once we do this, these R value reference transients start to compose. Transients don't really compose with the other API, because every time you put a function, you're putting a boundary where you lose the information about the locality of things. But with these things compose, so let's say you call say hi and pass result to say hi, there's not going to be any, any superfluous allocation in the call of these two functions, which I find really cool. This also means that the loop example can be rewritten such that instead of using dot transient, you can just use move when you're using the value v. All right. So I've been talking a lot about vectors. You can also apply these techniques to other data structures. Another data structure that the library includes is Hashmaps. And it uses the same principle of basically having a tree of big chunks. There is a very nice talk about immutable hashmaps by Phil Nash, the organizer of this conference. And you can watch it on YouTube. It's from CppOnSea 2017. Now, most of you will be probably asking yourselves, well, this is nice, but is this fast? And I have lots of benchmarks that I'm not going to go through. I'm just going to skip to the conclusion. Yeah, if you're interested in the benchmark data, I actually wrote a paper about this data structure and this particular implementation in C++. So there is a very systematic review there of all the implementation of immutable data structures of this style. And of course, this is the fastest ones. But I would say what's important here is to think, well, of course, some operations like updating the vector, you saw there is like a few allocations and copies of data. This is definitely slower than operating on an STD vector for the update, right? But one way to think about this is that you're amortizing these over all your copies that you're going to have of this data in your application, right? So instead of copying all the data whenever you need to look at the data, what you're doing is copying a little bit of the data when you need to update it, and then the copies are going to become effectively free, right? Because it's just copying a pointer under the hood. So this is going to change the way you architect the software, and it's probably going to be more efficient in different ways. For example, you're going to support more concurrency in a more natural way. And I still want to prove that this works in practice, so don't worry. I didn't show benchmarks, but I'm going to show a demo application. So to show how to use these data structures in practice, in the context of a whole application, I wrote actually a little text editor called ewig, which is the German word for eternal. And let me see. Okay, now I'm gonna need to look here. All right. So here I have a demo folder with a file that is 1 gigabyte big, right? Try to open this file in, well, don't try for sure in Atom or VS Code. It's gonna crash like almost immediately. In Vim, it's gonna be slow, very slow, but just maybe gonna be able to edit it. Let's try to edit it with this text editor. Oh, it's immediate. It loads in a separate thread. I can navigate the file. It's nice. It also supports UTF-8. Now, I think in other versions of the talk it didn't. Now it's loaded. Okay, let's go to the end of the file. There are 20 million lines of code here. You see like jumping and everything is super fast. I'm going to select all the text. I'm going to copy it. Wow, it was fast, right? And I'm going to, I don't know, jump somewhere. And I'm going to paste it 3 times. Oh, now we have, I don't know, 100 million lines. This was fast, right? So I think there is something about this data structure that is nice. I undid everything because now I want to show you something else. Now in the initial state again. And there is one little detail that I really like. I'm not sure if people at the back can see it, but here there are 2 dashes, which are the typical dirty marker of a text editor. So you want to see if you did any changes to the file, right? So I'm gonna do some changes. Oops. Okay. Demo problems. So I'm gonna do some changes. What's going on? What did it say? This is why I shouldn't have done changes yesterday. What? Now it didn't even load. Oh, yeah. And, okay, let's hope. Yeah, I did some changes last night, which probably shouldn't have done. Yeah, instance of bad variant access. Yeah, I think, actually, I want to prove it to myself because I'm getting really annoyed. Yeah, I think it's the last commit. But, okay, anyways, what I wanted to show is that when you edit the file, normally in a typical text editor, you get a dirty marker, which is a Boolean flag somewhere, and this dirty marker stays forever there, even if you edit the file using edit commands to a state that was the original one. In this text editor, and I'm going to use a smaller file now so it loads faster. Okay, so it really was that commit. I hope there is some lesson to learn here about nodes. Thank you. Okay, so yeah, here I can edit the file, and we see that the dirty marker turns into asterisks. Now, when I remove the characters I just introduced by using the space bar instead of doing undo, then suddenly the dirty marker disappears, because there is no dirty flag in this application. In this application, we just keep the previous states of the document all the time. If I want to see if there are any changes, I compare the current document with my current version. Now, this comparison is very fast, because even in the case where I have the 1 GB file, because as we saw, there is a structural sharing. So if the two versions of the document, they are derived by doing editing operations from the same original value, most of the tree is going to be the same. As soon as I see two pointers that are the same, I don't have to keep comparing inside that part of the tree. Right? Okay. So now we see that this works. Now we're getting into the part 3, redemption for the value-based architecture. Right? We're going to see how this text editor finally implements the value-based architecture in the way we wanted to do in the beginning, using this data structure. So if you wanted to build a interactive application like this text editor, or I don't know, Photoshop, or any complex editing software, or maybe even any view software, software with a UI, you will normally use this model controller view architecture, which is characterized by having this data model, which is the document you're editing, that is observed by some view, which has a reference to it, and then there is some controller, that sets up the view, potentially, sometimes not. Ideally, it's just, receiving the input and updating the data model with this. Now, this separation of concerns is very nice, and we should strive for this separation of concerns. But the problem is that the way this architecture is normally implemented, these boxes here, they are objects. They are locations in that mutable sense that we talked about before. The lines here, they are references between these objects, these mutable objects. The dotted lines, they are indirect references, because probably the view has a callback registered in the model, and this callback, of course, has a pointer to the view, so it can call it. So we have this graph of cyclic references between objects, which has one fundamental problem. It doesn't really compose. If you add more models, more controllers, and more views, you cannot simply put them in a black box and forget about them. If you have listeners connected to one update of the model, you cannot use this operation of the model in a bigger operation, because the things that are connected to the lower operation, they're going to see intermediate states. So to really understand the system, you have to understand everything that's in it. You lose the power of abstraction you get in the hands of the flying spaghetti monster. So there is another architecture that has been proposed by people from the web world, where people have really tried to simplify the architecture of interactive software. Everybody's doing like HTML, React applications these days. And they came up with this architecture called the Unidirectional dataflow architecture, which has similar boxes. There are these actions, models, and views. But what I like the most about this picture here is that the boxes and arrows mean different things. The boxes here, they are not objects. They are values. And the arrows here, they're not references. They are functions, transformations. So we have an action type and a model type and an update function that takes the model as a value, takes the action representing some input, some stimulus from the world, some action that the user did or wants to accomplish with the software, and then returns by value the new version with the updated state of the world. When we want to represent the things in the screen, we have a render function that takes the current state of the world and returns a view, right? For this last part, you normally need a system like React.js actually to be able to do it efficiently. You can maybe use something like an immediate mode API and achieve a similar result in C++ using a library like, let's say, imgui. Now, finally, you need to have some kind of way to deliver new actions. So there is a dispatch method that is kind of an stateful thing that is delivering actions coming from your streams of inputs from the keyboard or whatever you have. So implementing this architecture is really simple, but oh my God. Now that it's going to be a lot of code, I'm not sure we can really see like this. So, so basically the core of this application is in this function where this is code that was taken before I added the concurrency. We'll look at it later. Before we had concurrency, the main loop of the application was these 5 lines of code, right? So we have, or 6. We have the terminal object, which is a representation of, it's like n courses. So it allows me to draw and read from the terminal. Then we have the state. The state is the data model. And this is really cool because this variable state is the only mutable variable that there is in the program, right? Or the only mutable variable that lives through the scope of the whole runtime of the application. We initialize it with some variables, and then we say, well, while we are not done, we draw to the screen, we query what's the next action from the terminal. So this next thing will wait until you, let's say, use a key and return the action object that we saw in this diagram. Then we call the update function with the state and the action and assign the new state to the variable, right? This is the only really assignment that we have. Yeah, there is a question.
You're saying then that state is, you said before the state was mutable, but you're reassigning it there. So you're just reusing the same variable but still have a mutable state?
So the question is, do I have, am I reusing the same variable but still having an immutable state, right? And yeah, so the update function where my application logic is, this is a pure function, right? So this takes by value and returns by value. And it's just that I'm reusing this variable to, in the end the application moves forward and changes. So yeah, overrides the last value. Now, yeah. So to design the application then, we wouldn't do this by looking, at objects and their interfaces and their relationships. We will start actually by looking at the data. It's something a little bit like this fancy term these days, data-driven design, even though with a different purpose. So this is a more functional approach where we're not putting so much emphasis on layout and performance. We're putting just emphasis on what is the fundamental data that my application has that I need to be able to express the operations and actions that I want to express. So I'm not sure if you can see, but well, I'm going to try to read it for you. Here we have an index type and a coordinate type that defines positions in my editor. And then here is really the 2 most important types, at least for the purpose of this talk, which is align. And align is a vector of characters. And then there is the text, which is a vector of lines. Right? So we have actually 2 nested vectors. And this is what allowed us to do all these operations that we saw before, right? Because when I copy a chunk of text, I just have to slice it from these vectors. And then when I insert it, I just, put it in the middle through more slicing and concatenations. Then I have a file, which is represented by the name of the file and the contents of the file, of the loaded file. I have also something called a snapshot, which is the content of the editing state plus the cursor position. This snapshot is what allows us to do undo. So when we undo, we just keep here in this other type a vector of all the snapshots such that we can restore the contents of the buffer, and we can also we also store the position because you want to also bring back the cursor to where the user was editing at the time they did the operation. Here we have the buffer type. We say buffer, this term comes from Vim, and Emacs is, in all text editors, the document is called buffer. So this is the document where we have first a file called from, is the file we loaded it from, right? Which we remember has the contents of the file and the name. When we want to say if we're dirty, we check the current state against this content of the file we loaded it from. We have the cursor, the scroll position, and then we have some data for the history. We also have 2 coordinates with the selection. Then we have the application, which is basically the current buffer plus a clipboard and the messages that you see on the bottom screen. And then we have the action type, which for now, we will later evolve it, is just the key that was pressed, right? So it's a struct that contains the key. So this is nice because I think just by looking at this data, you can already easily imagine how a lot of the operations are implemented, I think, right? Like I don't know, if I tell you to implement a function that inserts a character where it's going to return a buffer, it's going to take an argument as an argument, a buffer, and the character you want to insert, and you're going to, return the update the content there, right? And I want to show you an example of an operation that is normally complicated, but in this case becomes simple, which is undo. Now, this text editor is inspired by Emacs, which is the editor I normally use. So it uses Emacs style undo. This is not necessarily, so doing a normal undo is more or less the same code, but I implemented this, so I want to show you how Emacs undo works. And the idea of Emacs style undo is that you never lose work. Normally, when you have an undo history, you do edits, you undo, and if you do a new edit, you cannot redo anymore. So you lose the work that was between the undos and the redos, right? In Emacs, basically, there is no redo operation. What happens instead is that when you undo, the undo itself becomes an undoable operation. So when you do an edit, you go to the end of your undo history, and then you can undo the undos you just did. So I'm going to show you visually. Let's say I do a bunch of edits here, right? So I do 3 edits, 4 edits, and I get 3 states of my document as 1, 2, 3, and 4. And the red thing here is the cursor that points to the current position in the undo history. Now, if I do an undo, the cursor moves 1 position back. As a user, I see the document in the state S3 again. But what we also do is that we push the state S3 to the undo history. If I do undo again, now I'm back to state S2, and S2 is in the undo history. Now if I do a new edit, now I'm going to do a new edit on top of S2. I get a new state S5, which is a derivation of S2, and we put the cursor at the end. So now if I start undoing, I will be able to also undo the undos I did, right? It's a little bit complicated the first time you use it, but it's very nice eventually because, I don't know, you can undo safely without worrying about losing all things. So how do you implement this? It's very little code, but it's even more little in these slides or in this projector. It's basically 10 lines of code for all of it. I'm going to try to describe a little bit of what's going on, even though you probably cannot see it very well. So there are 2 functions here, actually. The first is called record, and the second one is called undo. Let's look at the function record. The function record takes 2 buffers, the buffer before and the buffer after. So this is actually a generic operation that we're going to call unconditionally whenever any action that does something with the buffer happens. This means that we don't even need to know, which actions do an edit and under which conditions does the edit succeed. Like, for example, if I delete the first character, right? There is no new undo because the first character doesn't exist. The edit does nothing. This function takes care for all these conditions because the first thing that it does is to say, well, is the content before different than the content afterwards? If the content is the same, well, there is nothing to undo here. It just returns. But if the content is different, then it's gonna push the content before at the end of the undo history. Then it also checks if the history position is the same before and after. Because if the history position is different, it means that the operation was an undo. So it did something to the history position and we want to respect it. But if they are the same, it means that, well, we did an edit, we want to push the history to the end. So we actually use a null value to mark that the undo history is at the end. And this is it. This is all you need to do to record your undo operation. Then when you want to undo, well, we just look up what's the index of the history position, taking into account the possibility of it being at the end, which was the null value. And if it's a valid index, then we just query the content and the cursor position and set them in the buffer and return it, right? Now here, because these data types, they were structs, we do assignments, right? So we do normal C++ here, but these functions, they are pure functions because they take by value and return by value. So when I say I update the content, what I'm saying is I eventually return a buffer with this content updated, right? So yeah, this is all you need. And this is cool because also this doesn't even have anything to do with text editing. Like you can copy this in any program that supports undo and it's gonna work, basically. So this is pretty cool. I hope you're now convinced that the value-based architecture is nice. So we're gonna finally move to the part 4 of this talk, which is called embracing the value-based architecture. And we're basically gonna go a little bit into the details of some of the things that you can do with this. And I'm a little bit scared because there is more code here. So feel free to ask questions if my descriptions of the code are confusing or not enough. I think we're actually quite good with the time. So there is a question here.
You've been talking about pushback. How efficient is this for inserts in the middle of an array?
How efficient is this for inserts in the middle of the array? Well, it's way less efficient to insert in the middle of the array than at the end, because the middle of the array is basically 2 slicing. So what we do is we slice the vector into 2 subvectors. We push back at the end of the first vector, and then we concatenate these 2 parts, right? But all I do is pointers, yes, but I copy a significant amount of data because in particular the concatenation needs to still keep things balanced. So this is like logarithmic, like real logarithmic, because it's actually a logarithmic square, which is also logarithmic, but there's enough things happening on. So it's not as efficient as simply pushing back at the end. At the same time, in the text editor, I was also inserting things in the middle and all the time, and you didn't notice because, a tenfold factor in an operation that you do instantaneously is not that much. Of course, you have to be careful depending on how you're using this, right? So if you make a loop where you're inserting in the middle 1,000,000 times, that's probably not a good idea. You probably want to make a vector with these 1,000,000 things and then insert it in the middle by doing the slicing and concatenation only once, for example, right? So there are more efficient ways and less efficient ways to use this, and you have to be a little bit careful. Yeah. But But yeah, then again, with a standard vector also inserting in the middle, you have to copy all the data, right? So it's not bad, and it scales well in that sense. Okay, we're gonna go to the topic of side effects. Yes?
We're still on a break here. When you said you're comparing states for the document, how are you comparing the buffer? Is that a deep comparison?
So the question is, when I say I compare the states in the undo stack, yeah, how do I compare? Is this a deep comparison? And no, it's not a deep comparison, because all these states, they are derived one from the other. So the internal representation is all pointers, or not all of it, but most of it is pointers to the same data. So the comparison short circuits as soon as it sees that two subtrees are the same. This is why even in the case of this gigabyte file, it was working efficiently, even though as soon as you do something, it was doing a few comparisons of this kind. Of course, if you're comparing completely separate vectors, or even, let's say I load the file twice and compare it, then it's going to be slow because it doesn't, the data is completely separated in memory, right? Yeah, but if you can guarantee that there is a structural sharing, then basically the efficiency or the cost of the comparison is going to be proportional to the amount of change that you have between the two things. Right? Any other question before we move on? Yes?
So if I edit something, then I edit it back,
Mm-hmm.
I will have to leave blocks that are the same, right? Or will it recognize that this is a leaf block I've already had before and use it in the tree?
So the question is, if I edit and edit back, does it recognize that the two states are the same, and then do I have blocks that are different? Well, this is something you will have to do manually, for example. So when you detect that you are the same, then maybe you keep only one of those two. In my case, I don't do anything like that. So actually the two different vectors or the two document states that you're going to have in the undo history, they actually have a part of the tree which is going to be different, which is the part that you've been editing, basically. But yeah, you as a user of the library in this case could have the possibility of canonizing the representation, but just picking one of them and replacing one with the other, right? Okay, side effects. So how do we save the file? Oh my God. Okay, I'm gonna try something very hackery here. Okay. And now we just have to hope that it did something good to the code. It's a little bit better, right? And now I'm too far. Now I just have to read the text that is not code, but there is very, very little text coming. Okay. So now we're talking about side effects. You cannot see this part now. You have to make choices, you know. You cannot have everything. It's like, even though the topic of this talk was not making compromises, right? Like you can have performance and simplicity. Sometimes you have to make choices in life. Okay. So I hope it's a little bit better now. This is the save file function where I thought it's nice to see that, of course, now it's a little bit more complicated because it deals with UTF-8. This was one of the first versions of the function where I basically just open the file in a stream, and then I iterate over the content and save it. Now, I wanted to show this because the iteration is interesting. I'm not using normal for loops. I'm using this function Immer for each and Immer for each chunk. This is just for performance reasons. You can use the normal for loops and then it's going to use iterators. But since this is a tree, the iterator has to carry a little bit of extra state to know the path of the tree it's in. Iterating a tree is much faster when you do internal iteration. An internal iteration means basically you call a function like for each, you pass it a lambda, and then the for each does the iteration for you and calls your lambda back for each element, right? Somebody said you save some function calls. Yeah, well, you save carrying a lot of the states, maybe doing lookups for some of the things. Basically, everything becomes embedded in one traversal of the tree. And actually, when using this for each function, iterating over Immer vectors is on the range of like 1x the performance of iterating over STD vectors because of these chunks of data. So it's really fast. Now, there's the second function, which is for each chunk, which basically, instead of iterating over the elements, it iterates over the chunks of data, right? Because this data structure, we know, and it's one of its core properties that it stores the data in some contiguous chunks. So I thought it made sense to reveal this in the API as part of this function. So it invokes the lambda with 2 pointers to the beginning and end of the chunk. And this allows us, in this example, for example, to write directly to the file the whole chunk instead of each character with one call to all stream, which is better. Now, okay, so we have this save file function which saves the file, and then finally it returns the new file, which is basically, you remember the file data structure had the name and the content, so it returns the file name and the content we just saved. Now, in the update function of the application, we have something, this is a little bit of pseudocode. We will look later more in the details of this if, which is something like if the action is something like I should save the file now, then I save the file and the current buffer from, so where it was loaded from, is the file I just saved, right? So this will, of course, also remove the dirty marker, and I return the new state. Now, there is a problem with this, right? The problem with this is we said the update function is a pure function. This is not a pure function anymore. The update function now, see, now there is this nice blue here. This was meant to be like red, like, like this is not a pure function, and we really wanted the update function to be pure, right? So such that we can, for example, as part of a testing framework, just send it random states and see what comes out. We can compare what it did with what it did afterwards and whatnot. So how do we solve this? Well, this is the same function written but with more space because I'm going to put some lines in between. So this is the update function, and here we're invoking save file, right? And what we're going to do is, oh, now you cannot see the text. Maybe if I do. Well, I can just say this. So the solution is we're not going to perform the side effect we want to do. Instead, we're just going to describe the side effect we want to do. Okay? There are many ways we could describe the side effect. What is the simplest one? I will say it's a procedure. So a function that takes nothing, that returns nothing. It's a procedure. And this function is a value, right? Functions, they are values themselves. They're a bit tricky because you cannot compare them and, but they are values. So we are returning a value, which is basically the effect that describes the change we want to do instead of performing it. Now, to the function, we also pass the context. And the context, it could be many things. Basically, it could be access to subsystems where you're going to do I/O, right? But you don't want to pass to the pure function update. So update should not have access to anything that allows you to mutate the big parts of the system. You can put that in the context that is going to be passed to the side effect. So now the update function returns the new state and it returns the effect. So here in the save file function, what I'm going to do, well, I return this pair, the state, and I return a lambda that does what it was doing before. So instead of doing it, it puts it in a lambda and returns it. Now, well, when the file is done saving, we need to update the state of the application, right? In particular, we need to take this file that the saving file operation returned to tell us that it succeeded and put it as the in the from of the buffer, right? So the dirty marker disappears and we know that the file is done saving. Maybe we also want to put a message to the user or something. So the context has the dispatch method, the one we saw before. So we can dispatch an action from the effect to say, well, now we're done saving. Eventually, you need to reevaluate the update function. And then the update function implements in a pure way. It reacts to the save file done action by taking the file that was sent to it in the action and it stores it in as a current state, right? In this case, there is no effect, so we just return the new state and an OOP lambda, okay? Let me see. Okay. Good. Okay, so now we saw how to do side effects. This gets us to a second topic that I wanted to cover here, which is modularity. Well, the first thing that is worrisome here is that part of this is pseudocode. So there is something that is telling me to save the file. This could just be, checking that you press the save key, because the action was just the keys before. But then we also have some kind of action that is the file is done saving. And this is definitely not a terminal action. This is an action that we just invented to signal, you could say, this event, which is the event of the completion of the saving operation. Now it's funny because here I was using inverted code on each side. So here there is the action type that was the old action type that we have before, right? Which was, I can read the code here. This is the action that just contains the key code, and actually the size of the terminal is also part of it. But basically, it's an event that is just the key that you pressed. And this is not enough. We now have multiple types of actions. Actually here, I use this type called save file done action. We saw here there is a type. So probably we just want to put this as a struct. And we have now multiple structs that define different kinds of actions. So we have a terminal action, which is the action type that we have before. We have a save file action that describes, oh, I want to save the file now. And we have a save file done action, which is, well, saving the file is done. Now, these are different types. We need to put them together somehow. We put them together with std variant, right? So this is a type-safe way of saying the action can be one of these. Once this is an std variant, now we know how to implement these ifs, which is not using ifs, but using std apply. So we call std apply, and to std apply, we have to pass a visitor to visit the different kinds of things that can be there in the action type. I use an utility from Boost here. There is another version from Vittorio, actually, in the Celta library, which is a match function that allows you to create a visitor out of lambda functions. So basically, we just say here std apply match, and then we pass one lambda that says, well, if I have a save file action, I do this code. If I have a save file done action, I do this other code. And then finally also, if I have a terminal action, then I actually am going to return an effect that dispatches the save file action. I could also here call directly the update function with the action, but I like this because it separates what you could say user level actions from the intent. So you have what you could say your model, your application logic, business logic. You have the save file action, and then you're mapping it in this extra step, right? Also, if you had a way, for example, to generate actions, let's say from JSON files, you could trigger, in this case, the save file action without using the key command. So this is nice. Now, the other problem we see here is that maybe it's not so evident here because this application is relatively small, but here we're doing everything in the update of the application, right? And in real software, you're not going to have every action in the same huge variant and everything you can do in the application in the same update function, right? You're going to go crazy. You're not going to be able to work with other people, right? Because you need to be able to have modularity in your code to be able to work with other people, at least without killing each other. But there is one thing we can do, right? Here we have the notion of the buffer, right? And here we only have one buffer now, that is the current buffer. But one thing we could probably do is to, for example, be able to edit multiple buffers and have like multiple windows with multiple buffers. So we want to extract the logic of saving and loading the buffer from this function, right? Now, the first extraction operation I need to do is to extract it from the action type. I need to have one action type, in this case, the buffer action, that represents all the things that can happen to one single buffer. Now, the application, this is also an STD variant, the action for the whole application now, one of the things that it has is a buffer action. And it will dispatch it to the correct buffer when it gets it. Once we do this, we can extract the update function and have a separate update function that instead of taking an application takes a buffer, and instead of taking an action takes a buffer action, right? And it just has the same code that we had here. Now we put it in that function. Now still, we need some code in the main update function to deliver the buffer action to the correct buffer. In this case, we only have one buffer, so we call the update function on the current buffer, and then we say, well, the new state of the current buffer is going to be whatever the update said, and we also return the effects, right? Because the effects will need to be evaluated by someone. All right. So with that, I think we achieve a nice level of modularity. But we also introduce some elements here, like the context and the dispatching, which means that this code here is now not enough, right? We need to evaluate the effects that come from the update function. We need to have this context type that we're going to pass through the effects. And this context type needs to be able to, cause the loop to iterate. So instead of having this main loop here, now we have some code that you cannot see. But I'm using a library to turn this code, instead of an explicit main loop, have an implicit main loop, like the ones you normally have in when having a GUI library, right? So if you do Qt or GTK or any other GUI library, you have a run function, you deliver it to it, and then you have events that happen in this main loop. So here we have, in the first line, we have a boost ASIO IO service. Because we're dealing with the terminal, we can read asynchronously from the terminal actually using a boost IO service. To the terminal object, we pass the IO service, and then we have this call here called make a store. And to make a store, we pass it the action type, we pass it the initial state of the application, we pass it the update function, we pass it the draw function, and we also tell it, in this case, there is here some code that says with boost ASIO event loop, which says you want to use this event loop technology here. And this make store returns an object called the store. And basically this store object, what it does is take all these elements of the architecture that we saw, right? The data model, the update, and the action types, and the draw function, and binds them together. And it will basically deal with evaluating the different parts in the right times and providing us this dispatch function and everything. Actually here, in the next line, we have a function called term start, to which we pass a lambda that will be invoked whenever you press a key in the terminal. What do? We call dispatch and pass the key in a terminal action. We also, as a next step, call dispatch with load file, because now that we have a little bit of modularity, instead of loading the file like we did in the other code here, we load the file when initializing the buffer. Now, well, we initialize it with no buffer, and we call load file, which will trigger this asynchronously. And finally, we call run on the IO service that will, run the code until the user finishes. Now, this make store function is part of a library that you cannot see here. You can only see this part, which is maybe the most important one. It's a library called Lagger, which is basically Redux for C++. Because this model I was talking about actually is also reified in a very popular JavaScript library called Redux, which is used in combination with React. This is, you could say, a little experiment of bringing this to C++. And this library is now used also in the text editor to achieve this modularity, effects, and concurrency. One of the things that you can achieve with this is also time travel. Time travel? What does it mean? Okay, let me see. Oh my God, this is big now. So I have another version of the text editor here called evic debug. And now I can connect to localhost, and I can debug the editor that is running. What I'm seeing here, you see action and model. We're looking at the last action that was evaluated. In this case, was a resize action because I opened the new window. And we're looking at the states here. Now we can go here. There is another resize action. And here, finally, we have the load down action because the file was loaded. And we have the initial load action. And here we have the initial state, right? So basically, what this is doing is applying the principle of the undo thing that we said to the whole application and providing us a debugger to navigate the states of the application. Not only can I look at a JSON version of the document, I can also double-click and bring back the application to that state, right? So here, here is before we loaded the file, there was this state, then was this loading state. Oh yeah, I see what's happening because the resize is triggering new actions. Okay, here, oh, and this, okay. See, here we don't have Emacs style undo, we have the normal undo. So when new actions came, they replaced the other ones. So let me start again. What did it do now? Oh my God. Okay, I wanted to do this. Yeah, and you can see, that the loading marker came in and different things are coming in. And now I can, try to do something. And now it says can't edit what loading, but now we're locked in this state because the asynchronous effect is not, so the asynchronous operation is not happening, right? But I think this is very cool. It allows you, to see what happened, go back to a previous state, even continue working from this previous state. If you want to see more about this, time travel thing, there is a talk from last year at CppCon where I talk a little bit more about this Redux aspect. I also talked more about value semantics from a conceptual level, so about the design aspects of it. And I show you how the debugger is implemented and that the debugger can debug itself using the same techniques. Then finally concurrency, but I don't have much more time. Basically, there is the save file function that you saw. We can move the dispatch inside of the save file instead of the lambda that was outside. Then we can add some error handling by putting a try catch and dispatching some, something failed if something fails, and just put it in a lambda with an async, and now you're done doing it concurrently. Now you can also show the progress by, from time to time, dispatching an action that shows the progress. And finally, there is an async function in the context itself that will make sure that when you close the application, the asynchronous operation finishes instead of leaving the thread to its own thingy. Wow, this GIF is cool without the inversion of the colors, but now it's cool. Yeah, mind-blowing stuff. The conclusion. I really like this tweet from Andy Wingo. He's a compiler writer. I think he's contributed to V8, to SpiderMonkey. He's also the maintainer of the scheme implementation in GNU. And he says the following: to make a program slightly faster, you measure against each small change with benchmarks and only keep winning changes. To maybe make it a lot faster, you blindly invest a lot of effort on the basis of intuition and gut instinct, a weird dichotomy, right? And I think in the C++ community, we are very good at the first thing, right? Like, we start thinking about optimizing things, and then we make it very fast in the low-level details, make sure everything is using every tool nicely. With this, I hope I convince you that maybe sometimes trying to say, well, let's stick to the simple code and maybe do things in a different way, like using immutability, and using a data structure as a means to achieve the performance I want, instead of, getting this mutable mess to make sense, and then at the end being locked into some corner. Thank you very much for listening. These are the links to the projects I just showed. Yeah, thank you.